This is 141, cryptography. And by the way, I just calculated the point totals for the whole class and how many points you need to get a final grade of various types, because a student asked me about that last week. So you'll see that in an announcement in the Canvas. You can see how many points you have and decide how many more points you have to get an A or a B or whatever you want. All right. But we're going to start talking about hard problems. And I think I need to open it, so it's here. All right. So this is about as close as we get to actually covering any computer science in my classes, about which I don't know very much, but we'll talk about it in general terms. This is, as usual, like most of the math in this book, I'm only going over it in a sort of superficial way from an engineering point of view, how to understand what it means in practical terms, not the deep math of it. So we'll talk about computational hardness, and then the factoring problem and the discrete logarithm problem, which are important things to understand to some extent anyway. So computational hardness is a measure of how difficult it is to solve a problem, and that's the whole point of cryptography. You want to be able to say that I can use this cryptographic algorithm without requiring a whole lot of processing cycles and memory, but the attacker trying to break in without the key would never be able to get in because it would be so hard, it would take more computer cycles and more memory than they could ever afford to have. That's what you want to be able to say. So you want to have some kind of measure of how difficult processing is. So computationally hard problems are ones that take an unreasonable amount of time to solve, even if you have a lot of hardware like all the computers in the world or all the time in the world. That would be the best. So if you can measure the running time, and what you do is you just get a general estimate of it. You get a measure of how it depends on the scale of the problem. So if I'm just searching for a number in, say, an unordered list, I just have to try every element of the list. I'm searching for X in an array with n elements, so I just look at the first one. Is that it? Nope. Next, second one, is that it? Third one, is that it? And go until I find it or I don't find it. If I don't find it, I'll have to do n calculations. If I do find it, I'll do an average of n over 2 calculations. I typically get halfway through the list before I find it. So the expected value of running time is n over 2, so that's linear. If you change the size of the problem, the time it takes to do the processing will scale with it. If I double the size of n, I'll double the expected running time. All right. So that's linear, order of n. Now, if you're sorting a list that's unsorted, you have to do a lot more passes, and that's n log n typically. You can do it like sort it by the first digit and sort what's left by the second digit and a third digit, that sort of thing. So you have to do as many passes as there are digits, and that's log n. And then you have to do n passes, n calculations per pass. So that's the sorting. If you're going to do key recovery for one of cipher like AES, you have n bits in the key, and that means 2 to the n possible keys, and you'd have to try every possible key to get there. So it would be the order of 2 to the n, which is much bigger than either of these. This is linear, this is linear log, this is super exponential. Then there's quadratic time, which is in between, like n squared and n cubed and n fourth. Polynomial time is a smaller one. So here's these ones graphed. Here is linear. As the scale goes up, here is quadratic, and here is exponential, really fast. Yeah, why 2 to the n? 2 to the n because if you have, say, n bits, like 128 bits, oh, yes, if you did it with, you could write it in binary. It's just, that's why this, you're right, it could be log to the base 10 or log to the base 2 or log to base whatever algorithm you're doing. That's all. So, but the point is it will scale like the log. Yes, if you did it in base 10, then it would be log to the base 10 of n. If you did it in base 2, it would be log to the base 2 of n. Yeah. And then it would just be, there was also would end up approximately being the same because if the base is bigger, then the sorting algorithm is bigger. You know, anyway, that you're just getting the general rate at which it scales here. Yep, O notation. Yeah, it's very forgiving. This is what cosmologists do too. You just calculate the order of magnitude of the result. You're just trying to find out generally how big it is. You don't really matter if you're off by a factor of 2 or 5 or anything. You're just getting a general measure of how it scales. So polynomial time is n squared, n cubed, n fourth. They are considered feasible problems. That's not considered fast enough to make it impossible to solve a problem. Super polynomial is anything faster. like n 2 to log n or 2 to the n. Those are things that grow faster than polynomial. And of course, this is a sort of vague general term. Obviously, if n is large enough, then even linear you're never going to get there. So we're just talking in general terms here. So here is quadratic. Let's see, this is n squared. This is n to the log n, and this is 2 to the n. 2 to the n is really fast. That's why we like things like AES. That grows like 2 to the n, and that is considered really hard to get in without the key, and that's why we regard it as a strong cipher, where we have very strong reason to believe that nobody is getting in there without the key. All right, so there's time complexity, which is what we were just talking about, which is how many calculations you have to do, and that's related to how many CPU cycles and therefore how much time it takes. So that's time order. There's also space complexity. There are some algorithms that require a lot of memory, and then it would be how much more memory you take as you make the problem bigger. All right, so now we can get to the stuff that is a little bit mind-boggling, but suppose you define P as the class of all the problems that can be solved in polynomial time, all the polynomial time algorithms. NP is the class of all the non-deterministic polynomial time algorithms, so-called, and what that means is problems where you can verify a solution once you find it in polynomial time, but you do not have any way to find the solution in polynomial time. And these are, of course, the ones we like for cryptography. If you have the right key, you can use the key and it works, and that doesn't take very long. But if you don't have the key and you have to hunt for the key, then it takes forever. That's what we want. So we would like to have a nice, firm, theoretical, mathematical foundation for these NP problems, and we don't have it. As I mentioned many times, the problem with cryptography is you can't prove that things are hard. Not really very much at all. So all the stuff we use is not based on a very firm mathematical foundation at all. It's just based on sort of vague statements like, so far no mathematician has found a way to crack this, and it looks pretty hard. You would like to hope we'd have a better foundation than that, but we don't. All right, so NP problems, like I say, recovering a secret key with known plain text, so you'll know when you find the right key, then it's easy to verify, but finding the key is hard. Now there are problems that are harder than NP. For example, we talked about this before. Consider the one-time pad. If you use a different key for every letter in the message, and I give you the ciphertext, you can try every possible key, but then you will generate every possible plain text, and many of them will be perfectly readable grammatical plain text, and you have no idea which one is correct. So even if you have all the computers in the world and all the time in the world, you can never crack it. There's no order of anything. You'll never get there. This is very hard. This is not NP and it's not an NP. That's an impossible problem. And another one is verify that there is no solution. So suppose I want to prove that there's no way to factor large numbers into their component primes, which is something we imagine is true, and that's why we use RSA. Well, suppose you wanted to prove that there was no fast solution. You would have to generate every possible solution and see how long it takes, and prove that they all take too long. And that is another infinite problem. You could never get there. So there exist problems you can state that are even harder than P or NP problems. And then there are NP complete problems. These are the hardest problems in NP. Can I show the previous slide? All right, this one here. (13). All right. There, this one, right. So P is the things you can solve in polynomial time, and NP is the things where you can verify a solution in polynomial time, but as far as we know, you can't find that solution in polynomial time. Problems not in NP are also not in NP complete. Yes, NP complete is a subset of NP. So there are problems that are harder than either of these, but there is essentially no use. Those problems are essentially impossible. Yes. So, and this is, of course, the big issue. So P and NP are not all the possible problems in the world. What they are is all the ones that are really important to us, all the ones you can reasonably do on a computer at all. That's the issue. Very good. I'm glad you're asking these questions, because I've been struggling with this for years, understanding P and NP. It's a little bit of abstract algebra, a little bit difficult to grasp. All right, so NP-complete are the hardest problems in NP. And we don't know how to solve them in polynomial time, but they have proven that they're all equally difficult. And if you ever find a fast way to solve one, you can solve them all. And these are the famous ones, like the traveling salesman problem. If you have a set of cities on a map, what is the best way to drive from one city to the next to visit them all with the minimum total distance? That sounds easy. It turns out to be extremely difficult to solve because the number of possible routes is n factorial. And you really have to try all the routes and find the smallest, and that grows incredibly fast. The clique problem is trying to find, very much like that, if you have a map, you're trying to find the shortest path that connects 4 dots. In this case, you can see that it's up there. This is the longer path, but if the map is complicated, it's very simpler. There are various attempts to make approximate solutions using things like machine learning and stochastic problems, but they're not perfect. Yeah. Oh yeah, there are delivery companies do exist, and people just use simple algorithms. I know I had the same reaction when I first heard about this. In practice, you just do it, but you don't really know if you have on the shortest route. But you know, simple solutions. I mean, I think most people do it the way you play chess. Chess is also an extremely difficult problem, but you learn rules. You define like a score for your position. You try to avoid making obviously stupid moves. So if I was going to do it as a delivery man, I would plan not to ever go backwards, to kind of sort of go in a circle. And, you know, just make a sort of line that looked pretty good without a lot of zigzagging and figure that was pretty good. But you can't ever prove it's the most perfect one. That's right, delivery companies exist, but they don't really know if they're using the most perfect route. And, of course, for a small number of cities, like 10 or 20, then you can't actually enumerate all the possibilities, I think. Anyway, you can probably enumerate all the reasonable possibilities, but there are ways to do this. And the knapsack problem is another one I heard about, which I didn't recognize when it was in a capture the flag contest. They said, so you have a set of items. The one I heard in the capture the flag worked like this. You have a set of people that you might put on your hacking team, and each person has a weight and a skill. And your car can only handle so much total weight, and you want the maximum possible skill. So which group of people would fit within the required weight and have the maximum skill? That sounds easy, but it turns out to be just as hard as all the others. There are many possible ways to draw students from that pool that still identify the weight. You have to try them all. It turns out there's an awful lot of combinations. And so this is a similar thing. How do you pack a knapsack so you don't exceed the total weight, but you have the most monetary value of items in there or something? So anyway, these are all very similar problems, and these are the hardest possible NP problems. Yeah, that's right. Anyway, all right. So there are apparently these video games are NP hard. Tetris, Super Mario Brother, and Candy Crush. And there are some video games that are apparently even harder than NP complete. Now, NP complete are the hardest NP problems. But there's another interesting group of problems that are harder than that called NP hard. And therefore, if these are really harder than the NP complete, they are no longer an NP, because NP complete are the hardest NP problems. But they have not been able to prove that they're harder. What they've proven is they're at least as hard as NP complete. And if they're really harder, then they're no longer an NP. So there are things called NP hard problems. And I don't think I have an example of them, though. But anyway, those are the general categories of problems that computer scientists talk about. And so the issue is, this is actually a very interesting issue. I remember when I was a child learning arithmetic and mathematics, I noticed pretty early on what everybody else noticed. There are problems that are hard to solve. And then you take a math course and you learn how to solve them and you feel really smart. Like the original one was the original one was Gauss adding numbers from 1 to 100. And you can do it in 100 steps, or you can do it much faster by using a clever trick where you write it 100 and 101 the other way and see that there's 100 terms each equal to 101. There is a fast way to get to the answer. And this is the way all math is, right? There's a hard problem, but sometimes you can find a smart way to do it really fast. And then sometimes you can't find a smart way to do it fast. And so the question is there really a fast way to do every problem? There could be. How do you ever know? Or is it just that some problems are really harder than the others? That's the fundamental question here, and nobody knows. Some people think P equals NP, which means there is a fast solution to every problem, you just haven't found it yet. Other people think there really is a category of problems called NP that there is no fast solution. And that is what it seems like to most of us when you study math, and there's certain problems you just can't solve, but then every now and then somebody solves them. So you just don't know. I see someone's asking about kind of puzzles Google gives applicants. I don't know, might be the way I used to. And kidney donors, I would say kidney donors is a very similar issue, right? You have so many kidney donors and so many patients that need it, and you have some kind of measure of how healthy those people are, how young they are or something, and you're trying to somehow optimize the value of those donated kidneys. That seems to be the knapsack problem to me. Very good issue. Anyway, so someone's offered $1 million bounty for the proof that P equals NP, or that it doesn't, but nobody's been able to claim that yet. The stable marriage problem. Gee, I don't know about that. Seems to me like in a stable marriage you only have two participants. And if you could define what they both wanted, and if you could define how well they're succeeding at that, it wouldn't be that complicated a problem. Now, in my experience, the problem is that people don't know what they want. And they don't tell the truth, which is the hard part of that problem. Let's see, the stable marriage problem. Let's see. Okay. What's the stable marriage problem? Okay. Finding a stable, to match up all the notes, preferences between each element. So you each fill out like a profile with like 10, how much you like taking walks in the woods and how much you like hotels or something, and then you try to match all these parameters. Okay, given n men and n women, where each person is ranked all members of the opposite sex. Oh, this is where you marry the groups together. Oh, okay. That's basically what you have to face if you're running a platform like Tinder or something. Yeah, then that's the knapsack problem, I think. You're trying to match a group with another group, and it's complicated. When you match one pair, you can't use them again, and so you can't optimize the total happiness easily. Yeah, that looks like another knapsack problem to me. Yeah. Yeah. Just keep holding together one marriage together is another problem, which I think it's not a computational complexity. I think it has other kinds of complexity. Anyway, all right. So there's the question. Does P equals NP? Most people say no, which I think is why we have math books and textbooks and we give people Nobel Prizes and everything. We feel like when you find a good solution to something, that's an accomplishment. It's not that everything has an easy solution and there's no hard problems in math. There sure seem to be some hard problems in math, and it seems to be a huge accomplishment to find things. So this is the way most people think it is. P is a small group of problems that you can solve easily. NP is the problems where you can at least tell when you find the answer, and that's a big problem. And then there's the NP complete ones are the hardest, and there's problems like factoring that are not as hard as the hardest, but they're still pretty hard, and they're not in P. This is the way most people think it is. But nobody can prove it, because to prove that something is, in order to prove anything about this, you'd somehow have to prove that there is no algorithm that will ever be in polynomial time to solve this problem. And how could you prove that if something doesn't exist? That's hard. Yeah, that's right. Yeah, there you go. That's right. I had trouble understanding this topic. Like all the hard topics in these classes I teach, you just sort of hit it over and over like assembly code. First couple times it seems hard, and after a while you get used to it. Anyway, that's the way we think it really is, but we don't really know. And then, of course, there's quantum computers. Now, quantum computers have a different kind of processing than linear computers we've been talking about. They can do these weird things with qubits and entangle them and do weird information transforms that do not map simply on mathematical expressions. So they've now defined, you got NP and P, and then you got BQP, all the problems that quantum computers can efficiently solve, and they're trying to decide which of these problems over here quantum computers can efficiently solve. And we're still fighting about that. But as I mentioned before, we do know that this problem, which classical computers cannot solve efficiently, quantum computers can solve factoring efficiently. A pH, I don't know what a pH is. Some kind of generalization of NP. It's a good question. I don't understand it. There's a link here. You can try to understand it. God have mercy on you. But anyway, the quantum computers open a new group of these, and so people are currently in the early stages of trying to theorize what quantum computers are going to do to this. And we know they are going to change it. We know for sure this one is going to be moved into effectively P for quantum computers. This one is going to be understood. So it's going to affect these, and that's why we're all trying to discover quantum hard algorithms, and we'll be talking a lot more about that as we go on in the course. We're going to have to upgrade all of our public key systems within the next 10 or 20 years, because the current ones we have are all going to get broken by quantum computers. If quantum computers progress and get much better than they are now. So here's the XKCD. There's always an XKCD. So he goes to a restaurant with a different price for everything and just tells the waiter, I want $15.05 worth of appetizers. And this is the knapsack problem. Which combinations of these will add up to that? And I think it turned out that there were, in fact, 2 possible solutions. So, that's the thing. It's much harder than you might think it would be. All right. So if breaking a cipher were NP complete, yeah, that's right. And by the way, that also points out a good thing. For small cases, it's of course possible to solve anything, even if it scales badly. There's only so many possible combinations. All these things only get hard when the problem is when n gets pretty big, of course. When n is small, anything is solvable. All right, so if breaking a cipher were NP complete, that would be great, because then you'd know that breaking the cipher is the hardest possible problem. But the problem is those turn out to be miserable because they turn out to be easy in specific cases. So real cryptography uses problems that are probably not NP hard. That's why I like this diagram. You might like to use the NP complete or the NP hard ones, but those turn out to be so messed up you can't really use them. So you use ones over here in NP like factoring, which are still sensible enough to use, and you hope that they're pretty hard. You hope that the verifying the solution is NP, and you know that cracking it without the key is in NP, and you hope that the distance between these two is high enough that you've got a good cipher. All right. So the lattice problem is one of the NP hard problems that was the only one that's been used in cryptography. This is learning with errors. This one is unbelievable, and I really wanted to add it to this class, but then it got washed out in the quantum cryptography challenge, so I decided not to bother. There was actually like an online tutorial of how to do it in a simple case, and I started writing it up for this class, but I never quite got it ready. This was New Hope. This was Google's proposed cipher to survive quantum computers. And what it does is you take the input, which is like a megabyte of data, and you add random bits to it. You add noise to it. And then you do calculation on it, and then you somehow remove the noise. And that insanity somehow results in a form of encryption that cannot be solved on a quantum computer. So it is really mind-boggling. And that stuff is called learning with errors. And I got some comprehension of it to write the problem, but anyway, it got washed out. They made it to round 2, but it got washed out of round 3. So I'm going to wait for them to finish. In a year or so, they'll settle on one and make it the official new recommended thing, and then we'll learn that, whatever it is. But the quantum resistant cryptography does tend to be sort of mind-boggling. So it'll be something to bang our heads against when they make up their minds about what it is. Anyway, yes, meaning NIST did not approve it. What happens is a NIST has a call every time they approve anything like a hash algorithm or cryptography algorithm. They announce a challenge saying, okay, we're trying to define a new encryption algorithm, and it must meet like these 5 requirements. Then people send in candidates, like usually 40 or 50 of them, from private companies, random mathematicians, college teachers and stuff. They send it in, and then they argue. They publish them all, and then people argue and try to say, well, I hacked this one, I cracked this one. Some of them fall because they have serious flaws, and they're proven to be unsafe. Some of them fall because they turn out to be really hard to do on computers. Making it to round 2 is pretty good. That means it didn't have anything obviously wrong with it. Some of them got washed out of round 2 because they were similar to another, so they combined those 2 into one. I haven't been able to find an article explaining exactly what was wrong at New Hope, but it was not chosen to move to round 3, so it was not considered the best. Exactly how it failed, I don't know. If they ever have our conferences again, if we have B-Sides Las Vegas merged with PasswordsCon, and PasswordsCon was awesome. I went to PasswordsCon that merged with B-Sides Las Vegas about 3 years ago, and what they brought in was all the European cryptographers that wrote the encryption routines for passwords, and they gave talks on how all these things worked and why they were approved or wasn't approved. And I hope they'll do that for the quantum algorithms. I really like to watch some talks about what was the problem. B-Sides is always the same as DEF CON. It was canceled this year. Maybe it was remote only, but I think it was just canceled altogether. It always happens the same as DEF CON and Black Hat, which is in August. And I don't know if they still have PasswordCon associated with them, but I think they will, because that was pretty much a hit. And so anyway, I'd like to see the talks from the mathematicians explaining these various algorithms and how they choose them. But I think it's time for that when the quantum cryptography contest ends, which is supposed to be, I think, next year. B-Side San Francisco is coming. I just got a workshop approved there. We will be there doing this stuff, cryptography, as a matter of fact. So you guys will have already seen this stuff, but there will be other stuff there. Yep, that's coming around, I think, February next year or something like that. Anyway, so the factoring problem, the one we talked about a lot. If you have a large number n that's the product of two primes, find the primes. How difficult is that? Well, it turns out to be pretty difficult. Now, prime numbers are numbers that can't be divided by anything else, like 1, 2, 3, 5, 7, and 11. You can't divide it by 3 or 4 or anything, and get an even without having a remainder. These are not prime, like 9 and 15. They're the product of component primes. So here's a number that's the product of two primes, and you can find them because it's a small number. But if n gets big, this problem gets difficult. So the simplest algorithm is just try dividing it by every number from 2 to n minus 1, every number smaller than n, and see if any of them have a remainder of 0. That's one answer, and that will get you there. But if n is the number of bits in n, then this is order 2 to the n. That's a really hard problem. But there are smarter ways to do it. So this is why, like I say, most of us believe that NP is not equal to P. Hard problems are different than easy problems, and there are a variety of solutions to the hard problems. This is the dumbest way to do it. For 256-bit n, you'd need 2 to the 256 operations, which is, of course, wildly impossible. So try a better algorithm. Try only the primes from 2 only up to the square root of n. One of them must divide it if anything's going to. This is now 2 to the n over 2 over n, which is better than 2 to the n, but it's easier. This would be 2 to the 128. Oh, I see, divided by n. Ah, that's why this was 2 to the 120. I changed this. That's why it's 2 to the 120. Okay, good. I couldn't figure out why it was 0 instead of 8, but I missed this n here. So that will only take 2 to the 120 for 256-bit n, which is still impossible, but it's a lot faster. All right. And here, the general number field sieve is the best solution, which is fairly complicated, although I think you will program one if you do the crypto hack stuff. And this gets you down to 2 to the 70 operations for 1024-bit key and 2 to the 90 for 2048-bit key, which is why they now recommend 4096-bit keys to get 128 bits of security. So this algorithm is really a lot better, but all of those are very hard problems. All right. And so a 663-bit n was factored and a 768-bit n was factored. A 1024-bit n has never been factored yet publicly, although people suspect that the NSA can probably do it. And, all right, so that's why, most of us, they say we better be up to 2048 or 3096 or 4096 or 30, whatever it is, 3072, because this is to have something that we really think is uncrackable. All right, so is factoring NP complete? No polynomial time algorithm is known, so that means it's not in P, it's in NP. However, you can verify a factor once it's found, so it's in NP, but as that diagram showed, people believe it is easier than NP complete problems. And you would think they could at least answer that. The NP complete problems are the knapsack problem and the traveling salesman problem, and you would think you could at least prove whether it's easier or harder than that, but they can't even prove that. That's why this stuff is really hard to prove. And so, that's the story of this class. You would love if our cryptography is based on nice rock-hard mathematics, and it totally is not. It's based on sort of fuzzy, vague, unproven stuff. So there's quantum computers. This is a quantum computer calculating 7 times 13 mod 15. It's taking this number and factoring it to its component factors with these quantum logic gates connecting things. And so like a guitar, you feed in vibrations, and the interactions of these things cause the right answer to just appear at the other end due to the interaction of these without going through steps in an algorithm. It's just like a musical instrument where you feed in white noise and out comes a note because you have a flute or something that causes certain frequencies to get magnified and others to get removed. That's what this kind of thing is. One GPU year is a G flop over year. I think so. I'm not sure I understand the difference between a CPU and a GPU. I think they both do essentially the same kind of calculations, but GPUs are more massively parallel. But a GPU year would just be one GPU running in a year, however many processes GPU does. They typically talk in CPU years. And then they talk about GPUs in terms of many cores. Yeah, CPU, okay. Yeah, CPU year is not a GFLOP over a year. Oh, a gigaflop? Yes, if you want to look at it in terms of seconds, there's 3 times 10 to the 7 seconds in a year. So a CPU year is assuming some normal CPU speed. Yeah, and they say how many CPU years it took to do these things. Yeah, so 75 processing unit years, assuming something. I guess how fast GPUs were back then at probably 1 gigahertz. It's, again, a fairly vague measure because, as time goes on, the CPUs get faster, so CPU year is not a completely defined quantity. The flops would be more defined. A better way to measure it, really. All right, so you start from a problem that you assume is hard, and then you prove that it's at least as hard as some other hard problem. This is what you can do. So you can prove that one problem is related to another problem sometimes. So factoring and discrete logarithm problems are used as examples of a problem, and then you try to prove something is strong because it's as difficult as factoring or as difficult as discrete logarithm. That you can do sometimes, for what it's worth. Although you can't completely define how hard these problems are. So it's pretty shaky stuff. So let's talk about the discrete logarithm problem. This is actually fundamental to a lot of cryptography, and it's not that difficult. It's just a little bit weird. You do have to understand what a group is. A group is a set of elements and an operation that obey certain axioms. And so the simplest one, the one you usually use, is Z star P. Z star P is the numbers from 1 to P minus 1, where P is prime. So it's nice and simple. Z star 5 is 1, 2, 3, 4. And this number on the bottom always has to be a prime number, so that's the one you normally use. It does not include 0. And the reason this is just a set of numbers, but the set of numbers has nice properties, so you can define transformations that are useful for cryptography. It has these properties: closure, associativity, identity, and inverse, which we've all had in what we've done so far. We just haven't talked about it in these terms. So closure is when you perform the operation, which we call multiplication, on any 2 elements, you stay in the group. You never leave the group. This is why we use ring math. So if you have a byte, you transform it, you still have a byte. You never get some number that won't fit in the group. That's closure. Associativity means if you have 3 things you're combining, you can do it in this order or you can do it in that order, and you'll get the same answer. Identity means there is an identity somewhere, E, so when you take E times X, you get X. So there is an identity element like 1, multiplying by 1. Yes, this is typically, it's got to be a modular operation. You would never have closure unless it's a modular operation. If it was just normal multiplication of integers, you wouldn't have closure. The numbers would get bigger and go off the end. So typically, it's got to be a ring operation, yes. And then there has to be an inverse. So for every X, there is a Y that will give you 1. So there is an inverse. Now, so you can kind of see why you need this stuff for cryptography. You need closure because you want to encrypt bytes and get bytes. You don't want to get numbers that just get bigger and bigger and go off the top. You need inverses because you want to encrypt something by multiplying it by a key. There needs to be some way to decrypt it by multiplying it by something else that will be equal to 1. So you need some way to have an inverse of the operation. So you can see why these are the mathematical properties for something that would be valuable for cryptography. And that's what they call a group. All right. So there are commutative groups where you can reverse the pattern of operations. This is not strictly required, but it's true of all the groups I've ever used, that X times Y equals Y times X. All right. Now, there are cyclic groups, and these are groups where there is a generator, so you can take that to the first power, that to the second, that to the third, and you will eventually get all the elements in the group, which is pretty nice. So there is some way to generate them all. That's nice. That's another special kind of group. So now, the discrete logarithm problem consists of finding the decryption key. You have ciphertext G, and you want to know what power would you have to raise it to get X. This is essentially what we're saying. So what would you have to, how many times would you have to multiply this generator by itself to get that particular number you chose? Now we chose up here There is some power that will create every group, that group element. But to find that power, that's the logarithm. What is the exponent you need to get a desired answer? That's called the discrete logarithm problem. And this turns out to be as hard as factoring. Yeah, why is log x base g? Exactly, if you could do a log. But the problem is it's modular arithmetic. And I don't think you can even define a logarithm in modular arithmetic, just like you can't even define division in modular arithmetic. Remember, we talked about this before. All you can do is multiply. You can't undo multiplying by dividing. And you can exponentiate, but you can't undo exponentiation with logarithms. You have to define that operation, and it's not easy. That's why this is how you can encrypt something, right? Raise it to a power, and it will get scrambled, and nobody's going to get in there without the key because they can't find the power that would take it back. Yes, it's as hard as factoring, and factoring is NP, right? So factoring is hard. It has to be, if factoring were P, it would be useless, because then you could solve it quickly. So factoring is in NP, but you don't really know where it is in NP. And this is considered to be as hard as factoring. So let me go back to my diagram here, which I think is the most useful one. This one. So you have P, and you have NP, and you have the hardest ones here, and there's factoring, and the discrete logarithm is considered about as difficult as factoring. So they're both pretty good for cryptography. This is where the sweet spot is typically, where it is simple enough to use and hopefully far enough from P that you can trust it. These are too hard to use, and these are unsafe to use. This is the sweet spot as far as we know. All right, so that's the discrete logarithm problem. And that's it. All right. It is really the generalization. Now, by the way, if you want a mind bender, when I was an undergraduate, I was a teenager, I was taking like math and physics, but I was actually going to class and learning the stuff in the books. I lived with a guy who was a crazy genius. He was a rock musician, and he would actually flunk a class because he was at home studying a more difficult problem on his own. He was just very crazy and on his own path and disrespectful of authority figures. And he loved this stuff. He loved group theory and advanced mathematics, which I couldn't really understand very well at all. And then Rubik's Cubes came out. This was like the 1970s. And he solved the Rubik's Cube with group theory. And I still have only the dimmest comprehension of how he did it. But apparently the Rubik's Cube is a group. You have a state of those colored blocks, and you have a transformation where you rotate one side. That takes you to another state. It has closure. Your box doesn't fall apart. He figured out mathematically the solution for the Rubik's Cube. So you can do that. Yeah, music and math. Music and math are very similar. Absolutely. I wasn't even sure which one I wanted to measure in. I mean, music and math are very similar activities mentally. Anyway, I was not that great at that math stuff, so I never did that, but that's what he did. I did more experimental physics stuff. Anyway, all right, so things that can go wrong. Here's things that might mess up the world of this. The crypto hack guy, was he a musician? He might have been. Very often they are. Very much mathematicians tend to be musicians. Yeah. Anyway, there's an unproven theorem that you can solve every state of the Rubik's Cube in 7 moves. People believe that's true, but they haven't been able to prove it yet, last I heard. Anyway, so here's things that might happen. If somebody proved that P equals NP, and they found a way to find the fast algorithm, then everything would be shot pretty much. But this would kind of destroy the entire field of mathematics, and nobody expects that. All right. Then, if factoring got easy, now by the way, here's the problem. Some numbers are not easy. This is one serious problem with RSA. RSA sounds pretty good, but there are mistakes you can make when you choose the factors. If you choose them wrong, it's not safe. For example, this one here is not the product of 2 primes, it's the product of 4 primes, and one of them is pretty small. So all you have to do is start at the small numbers, and when you divide it here, it gets smaller, and when you divide it here, it gets a lot smaller, so you can actually factor this one, even though it's extremely long, because you don't have 2 really large factors. If P and Q are not random, and they're near a known value, then you can find it pretty fast. 20 moves have been proven. Boy, I don't know about that. Yeah, I've heard the claim of 7. Anyway, and then if you know something about P and Q, if you have some kind of leakage from a side channel where you know something about it, then of course that might make it easy to solve. Or if n is too small, like 128-bit RSA. That's not long enough. All right, and OpenSSL will let you generate really short keys like 31 bits. And of course, if you do that, they can easily be cracked by brute force. And the original RSA paper was from 1978, and at that time, they figured out that 512 bits, which was, I think, the 200 digits, was enough. That would take more than a billion years, and therefore it was uncrackable. So this is the problem. Computers get faster. So 512-bit keys was the original recommendation to be strong enough, and now we're up to like 4096 recommended. So that's another crazy thing about encryption. So you could have encrypted things in the recommended way in the 70s, and it wouldn't be safe anymore at all. So that's why people say you need a pretty big safety margin in cryptography if you think about the future. All right, and there's a couple more attacks in 2015 that came out. One is the Logjam attack, which is basically a side channel attack. This comes from export-grade cryptography. Because the United States banned export of cryptography, they had to make special versions of Microsoft Windows and every other product just for to be exported, which used weak cryptography. And now the world is poisoned with thousands of products and servers that have export-grade cryptography options. So if you alter the network traffic to claim that you are using a device running export-grade cryptography, there are a whole bunch of systems that will downgrade to export-grade cryptography, and that can be cracked. So that's the Logjam attack. This is why cryptographers hate this kind of restriction, where you poison the world with a bunch of weak crypto out there, and then forever after there's going to be unreliable crypto in use. And there's another one, a whole bunch of cryptography uses the same secret prime number, apparently. And they suspect the NSA has that number. So anyway, there's a link with more details about that. People use the same number for a bunch of cryptography, and people are afraid that was one of the NSA's poisoning activities, which they've certainly done several times. And so here's the Logjam. How many were vulnerable? This is from, I think, 2015, so 6 years ago now. And you see, like 8% of the top 1 million domains are vulnerable. And if you crack the most common 1024-bit group, it turns up to 20%. So a lot of websites are in principle vulnerable if you can trick them into using the export-grade cryptography. So that's not a fundamental mathematical problem, but it is a problem in practice. Logjam is tricking the TLS to downgrade. Export-grade crypto is something the United States caused by the United States government. And by the way, we just did it again this week. We just outlawed cooperating with NSO Group. They put them on a list of banned countries, so you can't sell them exploits. And in the days of Windows XP, like around 2001, the U.S. government banned exporting cryptography that was powerful. So you had to have a special weak version of cryptography in your products that you exported. So they made special versions called N versions of Windows XP, which we would export to countries that the United States did not like. And that used short keys and weak crypto. So forever after that, there are a bunch of servers using those products using export-grade cryptography. And therefore, when those servers connect to other servers, they have to downgrade their crypto to the old broken stuff to talk with the other servers that cannot talk good crypto. So if I can alter your traffic with a man-in-the-middle attack, you open a browser. Your browser might be Chrome, running on a modern version of Windows that can handle strong cryptography. But I could alter your traffic saying, I'm sorry, I'm running export grade IE from 2003. So you better send me export grade encryption instead. And that's crackable encryption. That's the fundamental problem. You can do the same thing by downgrading Windows versions too. But that's the problem. Now, zero knowledge proof, I don't really understand that. I've heard of it, the ZK snarks. It's a big part of Zcash, and I've heard explanations of it, but I don't really remember it. But I think in Zcash, where it's applied, the main point is you can verify that transactions have been authorized without knowing who authorized them. So the whole point of Zcash is it's incredibly anonymous. You can never prove who paid anything to anybody. But I don't really know in great detail how it works. These are good questions. Not that I can answer them all. Let's take a look at the cahoots. I think I might have to just open the Cahoots. Yeah, usually I got them open, but I think I got confused and didn't keep them open. Yeah. There's something called ZK Snarks, which I've heard a podcast about, but I don't really remember exactly how it works. But it's really very clever. The great thing about cryptocurrency is it's inspired all this brilliant mathematics. So 141. All right. I got to get it from here. They let me have folders now, which is great. It used to be really hard to find the right one. And I think we're in chapter 9. Okay. So 141. There we are. Let's run number 9. Okay. All right. And this is 9 hard problems. Good. All right. That may be enough. Looks like that's it. All right, what's the hardest complexity class? Okay, right, exponential. All right. All right, what's the easiest problem? P. Those are the easy ones. Good. Okay. All right. How about the knapsack problem? Okay, that is NP complete. It is the hardest NP problem. All right, how about factoring? That's NP, but it's not NP complete as far as we know. All right. All right, how long should an RSA key be for acceptable security? 128 bits. Yep, 4096 is the current recommendation. Good. All right. Yeah, that's what I mean. I just want to know the basic facts, not all the complicated stuff. Good word. Oh, I know who Goodward Alchemy is. I got that in my list. Enrique then, okay? And I think I know who all these people are. I'll have to look up my records, but I do know. All right. So, I stop this recording.